Hi everyone, this is video 10 of the Regents Chemistry curriculum, and today we're going to talk about thermochemistry. By the end of this video, you should be able to draw potential energy diagrams that demonstrate the absorption or the production of heat in chemical reactions. Here are a bunch of statements. Please read over them, determine whether they're true or false. If you don't know the answers to these statements, as usual, just wait until the end of the video and you should be able to answer them by then. Pause the video, look at them carefully, and let's get started. Okay, so thermal chemistry, the word thermal stands for heat. So we're going to talk about heat energy, how energy is gained, energy is released by drawing potential energy diagrams. So thermochemistry is the study of energy associated with chemical reactions. Energy can be in the form of heat, light, electricity. There could also be nuclear energy. There are all types of energy. Energy will always flow from hot substances to cooler substances. So if you have a hot pizza over here and you put your soda on top of the hot pizza, eventually your soda will be very warm, and your pizza will get a little colder. So very important that we recognize this acronym, BARF. BARF stands for if you break a bond or you go through decomposition, you'll absorb heat, or you need heat to break bonds. Take, for example, Al2O3. In order to break Al2O3, you're gonna have to add a lot of heat, and then you eventually will get aluminum and oxygen. Okay, and then you release heat when you form a bond. So obviously, going backwards, you're gonna have to release some heat in order to create the compound aluminum oxide. Okay, now always look at table I to confirm whether heat is released or heat is absorbed. You'll see in table I a lot of reactions, and here we see the delta H value, which is the heat of the reaction, and this shows us if it's negative, it shows us that heat is released, and if it is positive, it shows us that heat is absorbed. So here we have a reaction in which we're actually forming a bond, yet we're absorbing heat. So you can't really go by BARF all the time. However, you can always go by this table here. So always double check this table. If the reaction is not on this table, then you can probably assume BARF applies. Okay. Now, let's look at the potential energy diagrams concept. So a potential energy diagram gives us information about the energy released or absorbed in a chemical reaction in joules, kilojoules, or calories. You can decide whether you want to use joules, kilojoules, or calorie. Generally speaking, in Regents chemistry, we only use kilojoules or joules. That's it. Now, a potential energy diagram also indicates the heat of a reaction. Potential energy diagram, the potential energy of the products, and the activation energy of the reactants and the products. So activation energy is defined as the energy needed to drive the reaction forward, or in the forward direction, or in the reverse direction. So let's say, for example, Na plus Cl yields NaCl. So the activation energy is the energy needed to convert the Na and the Cl to NaCl. That's the activation energy of the forward reaction. The activation energy of the reverse reaction obviously would be the energy needed to be absorbed or released to convert NaCl back to Na and Cl. Okay, or Cl and Na. All right. The heat of a reaction is abbreviated delta H. It can be calculated by using the Pepper formula. So the Pepper formula is really potential energy of the products minus the potential energy of the reactants. The PEP minus the PER. Before I move on further, let me show you an example of a potential energy diagram. Here is what a potential energy diagram looks like. So letter A over here shows the potential energy of the reactants. This is how much energy is stored in the reactants. So in every reaction, there are reactants on this side and products on that side. Okay, so that would be a forward reaction. So this is how much energy is stored in the reactants, and this is the activation energy in the forward direction, from here to the peak, which is here. So from here, from this horizontal line to the peak, is the forward energy, is the forward activation energy. I like to refer to it as Phi. Letter D represents the reverse activation, represents the potential energy of the products. So here's your PEP, and this one would be your PER. So PEP minus PER will give you the heat of the reaction. And the heat of the reaction would be the distance between PEP and PER, which would be from here to here. Okay? So if this is the forward activation energy, or the energy needed to drive the reaction in the forward direction, this here from this horizontal line all the way up to the peak would represent the reverse activation energy. I like to refer to it as Rho. So that's your Phi ray. And the reverse activation energy is the energy needed to drive the reaction in the reverse direction. Okay? Letter B here will show the potential energy of the activation complex, which is really the potential energy of the entire reaction. Okay, that's the max energy of the reaction. Okay. Now, let's analyze this a little further. You want to determine whether this diagram represents an endothermic or an exothermic reaction. You simply look at it and you see how much energy was present in the reactants and how much energy is present in the products. Clearly here we started with so much energy that was stored in the reactants, and we ended with very little energy in the products. This shows that we have lost energy. And if you lose energy, you have an exothermic reaction. So think of exothermic as exit. Exit heat. So if you were talking about an exothermic reaction, these are the reactants, these are the products. So exiting heat, obviously the heat will be here. Kilojoules will be right here. If I was to draw a potential energy diagram of a endothermic reaction, here's an example. This would be a potential energy diagram of endothermic reaction because I started with only this much heat, but I ended with a whole lot more heat. This is an example of an endothermic reaction because it shows that I absorbed heat. You only started with 2 blocks or 2 squares of heat, and you ended with 3 squares of heat. Okay? This is pretty much the basics of potential energy diagrams. I'm going to just read along with you silently the rest of this stuff so we can have a better understanding. It's very important for us to understand that if something is releasing heat, it's going to make the surroundings hotter, but itself is going to get colder. So let's say you have a cup of coffee here, okay, and there's a lot of coffee inside. Obviously, if it's hot coffee, it's going to be releasing heat. So when you touch this cup, the cup is going to be hot. Why? Because the coffee inside is releasing heat. So this will feel hot, or the container will feel hot, but the coffee itself will continue to get colder, gets colder. Okay, so if I ask you whether hot coffee would feel hot or not, it actually would feel colder than the cup that it's actually containing. Well, it's going to get to a point where the temperature of the coffee, it's not going to feel colder actually. The temperature of the coffee is going to be equal eventually to the temperature of the cup. Because at one point, at a certain point, heat will not transfer from hot to cold anymore. Heat will just, if the temperature is the same, if the temperature of the cup is the same as the temperature of the coffee, heat will no longer transfer. Okay? And obviously, if something absorbs heat, then if, let's say, a coffee was absorbing heat, then the cup, the container, will feel cold, and then the coffee itself is going to feel very hot. That's if coffee was absorbing heat, so if the reaction was endothermic. Okay? Let's continue. Okay, very important that when we are looking at table I, if the question here, for example, if the question tells you how much heat is released or absorbed by 2 moles, by the synthesis of 2 moles of carbon dioxide, here we have a synthesis reaction, which we combine carbon monoxide, 2 moles of carbon monoxide with oxygen to synthesize 2 carbon dioxide. So in this synthesis reaction, reading it from left to right, we are releasing 566 kilojoules. So this reaction is exothermic. But if the question was asking you how much heat is released or absorbed by the decomposition of 2 moles of carbon dioxide, then obviously decomposition will be going in that direction now. Okay, so 2 carbon dioxide will be decomposing into oxygen and carbon monoxide. And because we're talking about decomposition now, we're going to have to actually flip this sign. So it will not be minus 566, it will now be plus 566 kilojoules will be absorbed upon the decomposition of 2 moles of carbon dioxide. Okay. So line A and line C are actually the same lines. Sometimes on the Regents, you may get a question that says, identify what C is. Don't get tricked just because C is not the distance between the x-axis and the first horizontal line. Don't get tricked by that. Just because it's not in the same place where it usually is, right here, it doesn't mean that it's something else. It's still the same thing. I could if it's the distance of the line that matters. So I can have this line right up here if I want. If this line fits between the first horizontal line and the x-axis, then this line will represent the potential energy of the reactants. I like to actually call this the peak, but I spell it with a C because it reminds me that it's the potential energy of the activation complex. It's also important that it's important to understand that sometimes you can speed up a reaction by adding a catalyst. Make a reaction happen very fast. We'll talk more about that in the next video when we talk about reaction rates. Okay, and you can make a reaction happen faster. And when you make a reaction happen faster on the potential energy diagram, you can show how a catalyst makes a reaction faster by lowering the forward and the reverse activation energy. So now the amount of energy will no longer be like that much. It will only be this much. And then for the reverse energy, it will not be that much. It will only be this much. So that's what a catalyst does. It makes a reaction happen faster by lowering the activation energy. We'll talk more about it in the next video. talked about that. We talked about that. Okay, so in this case, here, if each one of those boxes was 30 kilojoules, so the potential energy of the reactants would be 60 kilojoules, and then the potential energy of the products would be 90 kilojoules. So to calculate the heat of the reaction, it would be pepper. So that would be 90 minus 60, and you'll get your delta H to be 30 kilojoules. Positive delta H, again, means an endothermic reaction. So that's pretty much it for today. Let's go back to the questions. Here they are. Read the following statements, determine whether they're true or false. Pause the video, and have a nice day.